Alright, welcome to this video everybody. Today we're going to be talking about the congruence of quadrilaterals. Okay, we just finished talking about congruence of triangles, but now we're moving on to quadrilaterals. So a little bit more difficult, but and a little bit more revision from last year too for you. Okay, so for this one you'll want to, the learning goal is that students can identify the conditions for the congruence of triangles and deduce the properties of quadrilaterals. And at the end of this you'll want to be able to determine whether two quadrilaterals are congruent, and also want to be able to work some proofs on some quadrilaterals due to their properties. Okay, we'll see what proofs mean in the end. Okay, so a little bit of geometry revision from last year, just to get you on track with some of the skills and ideas, tools that you'll want to be able to use in this unit. So if I have an angle A, angle B, actually first, let's remember these things are called parallel transversals. Okay, so parallel lines, transversal is the line that goes across the two of them. Okay, so that's what we mean by parallel transversals. So we have angle A and angle B. So these are called co-interior angles. Okay, co-interior, and that means that A plus B is equal to 180 degrees. Okay, so that's the first one for you, and you would say that is according to the co-interior angle rule, which is a little thing that you draw like that to tell you that's the one you're using. Okay, let's have a look at this one here. Let's call this angle X, this angle Y. Here we would say that X is equal to Y because of, you might have known it as the Z rule, like that, but this is actually the alternate angle rule. Okay, the alternate angle rule. And the last one for you to worry about is if this is angle M and this is angle N up here, we would say that M is equal to N, and you probably learnt it as the F rule, like this. Okay, and that is called the corresponding angle rule. Corresponding angle rule. Okay, so co-interior, alternate, corresponding. Okay, so they only work when there's parallel lines in a transversal. Alright, here's some of the other ones, and these are different because these are just angles on a point. Okay, so these are all angles about a point. Okay, so the first one we've got is if there's a right angle, we would be able to say if this was angle A and angle B inside that right angle, we would say that A plus B equals 90, and use a little right angle rule there, and this one's called the complementary rule. Complementary. Now, complementary angles add up to 190. Alright, so here's the other one. If this is angle X and angle Y, here X plus Y would be equal to 180. Okay, and they would be degrees. They would be supplementary angles. Okay, so this is called our right angle rule, our straight line rule. So we draw a little thing like that to show we're using a straight line rule. This last one here, this one here is that, how am I going to draw this? Okay, so if I had some angles like this, I would be able to say, we had A, B, C, and D, I'd be able to say that A plus B plus C plus D is equal to 360 degrees, and you might have learned that's a lollipop rule, or the rule of revolution. So all the angles around a point are going to equal 360 degrees. Now lastly, if I had angle alpha and angle beta here, then alpha would be equal to beta because of our vertically opposite angles. Okay, so the angles opposite each other, opposite a point, are going to be equal. Okay, so those are some rules that you'll need to be aware of to be able to use in this congruence of quadrilaterals sort of section. Okay, so that stuff from last year, revise it, remember it. Okay, So some key ideas. There are some special properties of our different quadrilaterals that we've been looking at. Okay, so parallelogram. So there's the obvious ones that the sides are all parallel. So the opposite sides are equal. Okay, so opposite sides equal. Opposite sides are equal there. What else have we got? So opposite angles. So the opposite angles are equal. And the diagonals bisect each other. Okay. Okay, and so let's move on, have a look at the rhombus. So a lot of these are similar, especially since a rhombus is kind of like a parallelogram anyway. But a rhombus is a special kind of parallelogram where all of the opposite sides are equal and they're all sort of equivalent as well. Okay, so rhombus is all the sides are equal. Okay, the diagonals bisect each other, this time importantly at right angles, okay, 90 degrees. Okay, and the diagonals bisect our interior angles. Okay, so that means, all right, so that means that with this angle here, this half of it is the same as this half. So it's kind of like the diagonal chops the angle in half, all right? That's what bisect means. So when the diagonals cross here, that's why, so this side here, this length here is the same as this length here. That's what we mean by bisect. All right, so rectangle. Similar to a parallelogram, opposite angles, opposite sides are parallel and equal to each other, but we've got all 90-degree angles inside this time, and the opposite sides are equal, obviously, and the diagonals bisect each other, but not at 90 degrees with the rectangle. Okay, let's look at the square. The main special thing about the square is we've got all 90-degree internal angles again, and the diagonals bisect each other at 90 degrees as well. Okay, so important one to note there. Trapezium, not too much special about it other than has one pair of parallel sides, so none of the angles are bisected, none of the diagonals are bisected, so there's a lot. That's sort of the weird one of the lot. Okay, and our kite, finally, let's just move this text out here for ourselves. So we've got that one pair of the opposite angles are equal. So that is this one here and this one here. Okay, they're equivalent to each other, but the opposite ends aren't. The diagonals intersect at 90 degrees. So notice I said intersect there because they're not perfectly bisected because only one of them. So this diagonal here gets cut in half by the other one. Okay, all right. So what's all this going to be used for? Well, let's have a look at an example. We're going to try and prove that the diagonals of a parallelogram bisect each other. Okay, now you might be wondering what that means. Again, so what we're trying to do is we're trying to prove that this length here from O to C, okay, is the same as O to A. And similarly, B is the same from B to O, and O to D is also the same. Okay, so let's look at how we're going to do that. So we're going to outline something called a proof, which means that we sort of create evidence based on what we can prove and then move on to our conclusion. So the first thing we're going to say is that angle ACD, which is this big one, A to C to D, angle ACD is equal to angle CAB. Okay, so what I've said is that this angle here is equal to this angle here. Okay, because of the Z rule. Okay, alternate angles. Okay, and I'm going to also make the statement that angle CDB is equal to angle ABD because of the same thing. Okay, and so that one is this one here. Okay, so I've said that this angle is the same as this one, and this angle is the same as this one. All right, because of our alternate angles, we're allowed to do that because we've got that diagonal is like a transversal across two parallel lines, same as that one's also a transversal across those two parallel lines. Okay, now we can also say that we also have that CD, so this line up here is equal to this line down here, BA, okay, because it's a parallelogram, and that's one of the functions of a parallelogram is that our opposite sides are equal, so that's okay. All right, therefore, so I've said that this is equal to this, okay. Now you'll notice that what have I got in here? I'll draw it in blue, I've got a triangle here and a triangle here. And I've just said that it has equal angles, so two sets of equal angles corresponding and a corresponding equal side. So that means I can say, therefore, triangle CDO is congruent to triangle BAO. Okay. All right. Now that if that's the case, therefore line BO is equal to or equivalent to line OD, and line CO is equivalent to line AO. Therefore, diagonals bisect. Okay, and I'm finished. Now, that might seem very complicated on first reading, but I encourage you to have another read through it. Try and have a go yourself. There's some examples of that kind of stuff in your exercise and your text for you to have a shot at. So that's pretty high end up there mathematically. A little bit of logic, bit of argument, making your case for why that is happening inside that shape. All right. So have a go, give it a shot, and any problems, issues, please come see me at school. All right. Thank you very much.